Hello legacy students, Marsh here. So today we're going to look at exponential growth and decay models, the real life examples, so basically the story problems behind those graphs you were just graphing. We're going to want notes, pen or pencil, and then a calculator as well today. So very first thing, exponential growth models is compound interest. Now every single one of you at one time in your life are going to have what's known as a savings account. So this savings account, this is how that money grows, how you find interest, okay, and how you know how much money you're going to get after a said number of years. So this formula, A equals P times the quantity of 1 plus R divided by N to the N times T power. That is the formula that's going to get you how much money you're going to make after so many years. Now you're probably saying, Marsh, that's a lot of random letters. What are we going to use? Well, this is what these letters stand for. So P is the initial amount deposited. A lot of the times you'll be told that this is your principal amount. Okay? R is the interest rate. Now, highlight this, star it, I don't know how, whatever you need to do here. Expressed as a decimal, because you do need to make sure that that 35% is as a decimal. Now, something to keep in mind. If it's 35%, guys, best way to get this to convert to decimals, either A, move the decimal twice from the back, so this would be 0.35, or you can do 35 divided by 100. That'll also get you the 0.35. So either A, move the decimal twice to the left, or B, divide it by 100, and then you'll get the decimal for it, okay? N is the number of times compounded per year. Now, N can take different depending on what the word is in the problem. So semi-annually, that is twice a year. So it's going to compound twice a year. Quarterly is 4, because there's 4 quarters. Monthly, 12 months. 52 weeks, and daily would be 365 compound. What that means, that is the number of times that the money you're going to gain interest in that year. So most of the time you'll find that monthly would be a common amount or common compounding amount, because that's usually how your savings accounts compound. T is the number of years, so that's the number of years you're going to leave it in there. And then A is the balance after T number of years, depending on what that is. Let's take a look at an example of compound interest. You're going to definitely want to write these down, okay? You deposit $2,900 in an account that is 3.5% annual interest. Find the balance after 2 years if the interest is compounded monthly and weekly. So what I'm going to do, guys, is underline all the words, or all the stuff I know that I need. 2,900, 3.5%, I need 2 years, and I'm compounding monthly and I'm compounding weekly. So I'm actually going to have 2 problems. One monthly, one weekly, and we're going to see which one gives me the more money. So, first of all, compound monthly. So my P, or my principal, is the initial amount. So that's the initial amount, 2,900. And then 1 plus my rate. Now my rate has to be as a decimal. So 3.5%, that's as a percent. So if I move it twice to the left, I'm going to get 0.035 divided by N, number of times compounded. I'm compounding monthly, right? So this would be 12. And then it's N times T for your exponent. So my N is 12. Times the number of years, T, which is 2, compounding for 2 years. So now, guys, this can go straight into your calculator. You might need to do some exponents. I would definitely recommend, instead of doing 12 times 2, typing in 24 for the exponent. Definitely have some parentheses around here. You should get $3,109.96. Okay, let's try weekly now. It's going to be basically the same setup, right? Because I'm still depositing the same principal. I still have the same interest rate. But now my N is going to change. It's no longer going to be 12 because I'm compounding weekly. So weekly would be 52 because there's 52 weeks in a year. And then it will be 52 times 2 out here. Now, guys, this itself is 104, so please make sure you simplify that before you type that into the calculator. So I will get $3,110.20. So actually, it does not pay for me to compound weekly. It's actually not much more than a couple of cents. Now, let's take a look at a growth model. This is when we are not dealing with compound interest, when compound is not in the problem. So you're going to want to make sure you write this down and make sure you know what each letter stands for. So A, guys, is the initial amount, so that is the principal or the starting population or something along those lines. R is the percent increase, so that's like the 3% increase for 5 years kind of thing. Expressed as a decimal again, guys. And then T is your time. So now 1 plus R is going to be the growth factor, or the factor that the population is growing by. So let's take an example of population. So I have this initial population of 38 buffalo in this state park. In the population, they're growing about 7% each decade, which means every 10 years, right? Write an exponential growth model and estimate how many buffalo are in the park after 70 years. So I'm going to underline here, guys, all the numbers, because obviously those are going to help me. So now let's plug it into our formula. So I have y equals A. A is the initial amount, which I start with the initial population of 38. So it's going to be 38, 1 plus my rate, and my rate is 7% each decade, so 0.07, right, would be a decimal, and then times t, or to the t power. Now be careful, guys, this is not 70 years right here, because I have 7% each decade, so I need to make sure that the each blah 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 matches my time given, because right now this is talking decades, this is talking years. Those aren't the same thing. So let's convert years to decades. So would you guys agree with me that this is technically 7 decades worth of time, right? 70 years is 7 decades. So I can actually put for an exponent as 7. So once I type this in my calculator, so basically I can do like this, 1.07, right, to the 7th power. I now have approximately 61 buffalo in my state park after 70 years. Only that much grew. Now, what about going the other way? Decay. So decay model, same thing. It looks exactly the same like growth, but you're actually subtracting. So growth and decay look exactly alike. So it's going to be A is your initial amount, R is the percent decrease. Please, guys, please, expressed as a decimal. T is for time, so 1 minus R is going to be your what's known as your decay factor. Now, you guys may have heard of depreciation before, especially with cars. Depreciation means go down in value. So if you ever heard that you lose value on your car when you drive it off the lot, let's take a look at how much you actually do lose. So I got this new car and it's going to cost me $25,000. The value of my car is going to decrease by 23.5% each year. That is a lot of decrease. So let's write the decay model and then let's estimate the value after 4 years. So I got 25,000, 23.5%. So it's going to be y equals my initial amount, which is what I'm starting with, 25,000, 1 minus my rate as a decimal, which would be 0.235. And then that would be to the t value, right? So this would be my model that we're going to follow. And now what I'm going to do is plug in 4 for that. So 25,000 and 1 minus 0.235 is actually 0.076 or 0.765, excuse me, to the 4th power. So once I do that, I actually get, for my car, after 4 years, it is only worth $8,562.21. Only 4 years old, and my car is worth under half of what it was worth originally. And that's the end of this video. See you later, Sabres.